Yeah. Good morning, sir. Can you hear me? Uh,
Yes,
Try to
yes.
unmute yourself. Suresh, sir, you're mute. Yeah.
Yeah. Now it is audible.
Yes, yes, it is. It is. It is.
Yeah, thank you.
Okay, so we'll just wait for 2 more minutes. Let's the participant join and then we'll start. In 2 minutes,
Yeah,
we'll.
sure,
Okay.
sure,
Thank
man. Mm.
Okay, very good morning to everyone, and I welcome you all to the first session of the second day of the workshop. And it's my pleasure to introduce the first speaker of the session, Dr. Suresh R. So I would just like to brief about him. Dr. Suresh is working as an assistant professor in the Department of Statistics at Bangalore University. He did his MSc and PhD in statistics from Bangalore University, and he has more than 8 years of postgraduate teaching experience and has sound knowledge of R and SPSS. Published 15 national and international publications, and also co-authored a book with Dr. Prabhanjan and Dr. Manjunath on R. And the book is titled as A Course in Statistics with R, and it is published by John Wiley. I'll mention the reference in the chat box for the reference of the participants. And his areas of research are time series analysis and regression analysis. And I would like to thank him that he has accepted our invitation on a very short notice and accepted to prepare a session for this. So, with this short introduction, I would really like to welcome sir and please start the session. Thank you so much.
Yeah, yeah, thanks for your nice introduction, madam. Good morning, everyone. Okay, let me start my
Wonderful.
presentation. Is the screen visible, madam? Is it?
Yes, sir. It is. It is.
Yeah, I'm trying to present. Just few minutes so that I'll set these things right. Yeah, how about the screen now? Is it visible?
Yes,
Yes,
sir. It is.
yes, sir.
It
Yes,
is.
sir. Yes.
Yeah, the slides are
Yes.
visible, right?
Yes,
I have
Yes.
yes,
Yes.
displayed the slide. It is on the screen.
Yes, yes, yes.
How about now? Now
console.
what is visible?
Yes.
Our console is visible, right? Uh,
Yes, sir. Yes,
shall we
sir.
start?
Yes, sir. Yes, sir. Definitely.
Yes, sir.
Can I start, madam? Yeah, good morning. Yeah, good morning. See, since I have been asked to address or speak on some parametric tests, I'll be speaking on some of the very standard tests of significance that we usually use, and this will be demonstrated using the software. When it comes to my presentation, I see I'll be toggling between two windows, two or three windows. One will be my presentation slide, which contains materials, and the other one is the uh, R software, R window. And in this R window, I have two windows inside that. One is the console, and the other one is the already written codes. Are you with me? Hello?
Yes, sir. Yes.
Hello? Hello? Yeah. So this is
Yes,
how.
sir.
So whenever the situation demands me to use our software, I will switch over to this software and I'll execute the commands, and the output will be explained. So that is how, okay, I have designed my talk. Is it okay? Yes. Yeah, this is the outline of my talk. First, no, just to what is it? For the sake of completeness, since it deals with testing of hypothesis, that is test of significance, some important parametric tests. I'll quickly recap the basic things corresponding to testing of significance. That will be my first topic, and that it will be followed by some important tests. I have chosen seven commonly used tests for today's topic in this talk. Yeah, testing of hypothesis. Why should we test an hypothesis? In any research, the key questions to be answered are generally expressed as a statement of hypothesis that has to be verified or disproved through experimentation or survey. Now, how do you get this hypothesis? These hypotheses are suggested by past experiences, observations, and at times by theoretical consideration. And to address these hypotheses, statistics provides logical tools so that you can take decisions in the uncertain environment. And these will be done in the framework of inductive logic. And test of significance is a branch of statistics that provides tools to decide the nature of the population from the information contained in the random sample selected from it. So from the sample, we move on to the population. So hence, that is what is inductive logic. And since when you're when you're moving from the sample onto the population, okay, we come across randomness, and hence the inductive logic will be carried out in the framework of, in a random framework. Some concepts what we very commonly come across in testing of hypothesis: population is nothing but the set of observations, individuals or items relating to a phenomena under statistical consideration. And when it comes to sample, it is a portion of the population. Parameter is nothing but I have a characteristic pertaining to a population which I am interested in. This characteristic is okay. This characteristic can be described by a measure, and that measure is nothing but parameter. That is what we call in statistics. The descriptive measure of a particular characteristic is called of a population is called as a parameter. And in statistics, we come across many population parameters like population mean, population variance, population proportion, population correlation coefficient, and regression coefficients beta. And where the counterpart of that in the sample counterpart of that is nothing but is known as a statistic, which is nothing but a descriptive measure computed from the sample drawn from that population. Then statistical hypothesis is nothing but a statement made regarding some characteristic of a population. Usually we express this in terms of parameters of the probability distribution of that characteristic, say y, and which is to be verified for its truth. If the statistical hypothesis completely specifies the distribution, then such an hypothesis becomes simple hypothesis. Otherwise, it turns out to be a composite hypothesis. Again, we have two types of hypothesis, that is null hypothesis and alternative hypothesis. The hypothesis of no difference or null effect is called a null hypothesis, and usually it is denoted by H naught. And we test this for its possible rejection under the assumption that it is true. When it comes to alternative usually most of the times the null hypothesis contains equal sign. When it comes to alternative hypothesis, it is the hypothesis which is against formulated against the null hypothesis. It's a counterpart. It is an opposite of the alternative hypothesis, and it is denoted by H1. And this is the hypothesis that is believed to be true by the researchers. Sometimes it is also called as researchers hypothesis. And in example 1.8, you can see some of the hypothesis. There is a spelling mistake. Sorry, SCS. It should have been. I have H naught. This hypothesis pertains to the population parameter. Hello, hello. Am I audible? And is it clear?
Yes, yes, sir. Yes, sir. Yes, sir.
Yes. Okay. Some hypotheses I have listed here. Again, we have concepts like one-sided test, two-sided test. So what are these? A significance test for which the alternative hypothesis is directional. For example, if in case in the previous on the previous slide, if in the third first itself, if you see that the alternative hypothesis is mu less than 25. This amounts to this such an hypothesis called as a one-sided alternative hypothesis, and it is left-tailed. And similarly, if in case this were to be greater than, then it would have been one-sided and right-tailed test. Suppose there is no direction. Say with respect to this example 2, it is clear that the alternative hypothesis says that the mean is not equal to 22. Such type of hypotheses are called as two-sided alternative hypothesis. Now the choice between one-sided or two-sided that should be made before any test statistic is calculated, and it depends on the objective of the study. Now to carry out this test, we have to carry out to conduct this test, there is a rule, and that rule is called as a statistical test. It will be based on sample observations, which will be used not to reject the hypothesis or reject the hypothesis. Then see, whenever we do that inference, say based on the sample informations, we are trying to generalize on the results onto the whole population. We are prone to commit mistakes. So in testing of hypothesis, there are two types of errors that can be that one would come across. Those errors are named as type 1 error and type 2 error. Type 1 error is nothing but the hypothesis may be true, but actually we are rejecting it. So it is probability of rejecting H naught given that in fact it is true. That is type 1 error. And type 2 error is we are not rejecting the null hypothesis given that the alternative hypothesis is true. And these errors can be measured, and they will be measured in terms using a probability. And the probability of type 1 error is denoted as alpha in the, we have a notation to denote that probability of type 1 error, that is alpha, and beta is the probability of type 2 error. And we usually fix this alpha well in advance before conducting the study. In most of the cases, either it will be 5% or 1%. Then when it comes to level of significance, we have a concept notion called as level of significance. That is the maximum probability alpha of the type 1 error fixed in advance. So that is, say if you fix alpha is equal to say 5%, then that 5% is called as the level of significance. Yeah, the same thing has been tabulated here, the errors in hypothesis testing. And this beta 1 minus beta is called as the power of the test, that is rejecting H naught given that it is false. Now apart from 5% and say 5% and 1%, there are situations wherein the alpha will be fixed 10% at 10% or even 2.5%. There are studies. This 10% is very common in social sciences, whereas in medical and other field, we in fact adhere to more less than even 1%. Now critical region is nothing but the set of all possible values of the test statistic. You use test statistic. It is nothing but a rule, either to reject the hypothesis or do not reject the hypothesis. This test statistic, okay, the set of all possible values of this test statistic, okay, will lead to a concept called as it leads to the rejection of the null hypothesis, and such a region is known as a critical region or rejection region. And then a critical value is nothing but the test statistic. Whenever you calculate a test statistic, you compare that test statistic value with the a value, and based on that value, based on that comparison, you take the decision. The one with which you compare the test statistic value, that value is called as critical value, and the value is related to a particular significance level chosen, and even it depends on the the distribution of the test statistic under the null hypothesis. And the counterpart of this critical region is nothing but the acceptance region, means the set of all possible values of the test statistic which leads to do not rejecting the null hypothesis, is nothing but the acceptance region. Then under this testing of hypothesis concept, we come across a notion called as sampling distribution. Sampling distribution is nothing but the probability distribution of a statistic, and corresponding to such a statistic, in the sampling distribution, every sampling distribution will be having corresponding to a sampling distribution, we do have a standard deviation, and that standard deviation of the sampling distribution of a statistic is known as standard error. The standard error is very important in testing of hypothesis. And another important concept which we generally come across is the p-value whenever we conduct tests of significance or testing of hypothesis. This p-value is used in hypothesis testing so that we can either reject or do not reject the hypothesis. It is nothing but the evidence against the null hypothesis. The smaller the p-value, the stronger the evidence against the null hypothesis, hence you should reject it. Smaller the p-value, more significant the results will be. Sometimes usually the p-values will be expressed in percentages also. We have seen some in articles as well. And the rule is that if p-value, see, you compare this p-value, there are two ways of taking the decision. You either calculate the test statistic value, obtain the test statistic value, compare the test statistic value with the critical value, and take the decision. This is one approach. The other approach is based on the test statistic value and the corresponding null distribution of the test statistic, you calculate the probability, and that probability is called as p-value, and you compare this p-value with the chosen level of significance. If in case it is less than the chosen level of significance, p-value less than the chosen level of significance, then you reject the hypothesis. Otherwise, you do not reject the hypothesis. So most of the notions, whatever notions, important notions that is required to discuss tests of significance, I have just now revived those concepts, and the same notions have been listed on this slide. Now, if you take any hypothesis testing problem, it has usually tests six steps. Number one is you need to set up the hypothesis. Hypothesis means alternative as well as null and alternative. And corresponding to this, there will be some assumptions that will be specified, or the entire test procedure have been built upon. So you need to be aware of the assumptions as well. So sometimes you need to verify the assumptions. So for these assumptions also, validation of the assumptions has to be done. So that will be the first step. Sometimes what happens is that without conducting the test, you'll be not able to verify the assumptions. So even that will be also the case. There are some cases wherein you need to use this approach. The second is you specify your level of significance. That is nothing but alpha well in advance. And then you calculate the test statistic. That will be the third one. Now, once you calculate the test statistic, now you need to find the rejection region or calculate the probability value. This probability value will be calculated using the test statistic value, and the rejection is found by using alpha, and hence find a critical value. Now take the decision, either reject or decide not to reject the hypothesis. And once you do so, the last step will be to draw the conclusions. Hello. So I'm through with the basic things that are required to discuss test of
Yeah.
hypothesis.
Yes, sir. Yes, sir.
Shall I proceed?
Yes, sir. Yes.
Yes.
Yeah. Yes. Okay. So this is the slide which contains the important commonly used tests of significance. I mean parametric. Some seven I have listed here. The first is see all are related to means. Similarly, we can discuss pertaining to the proportions also, but due to the time since due to what is the time constraint, I'll be not doing so. I'll adhere only to the mean and see. Okay, in between we come across tests related to other aspects also, which are related to the assumptions pertaining to these tests. We'll discuss them as well. So first will be mean of testing related to mean of one population. That is nothing but Z test, which is the last sample, and we assume that the variance is known. Either the variance is known or it would be a large sample. Then we'll extend this idea to two populations. Means I have two means pertaining to two. I have two populations. I am interested in testing the equality of those two populations, means of those two populations. Again, I assume that the sample size is large or the variances of both those populations are known, and that will be followed by the mean of one population, the small sample, so hence the t-test. And again we'll extend this idea to two independent populations. Then comes paired what is it? Yeah, here there are two cases assuming variances are equal and variances are unequal. The next will be two dependent population, that is nothing but the paired t-test. The last one will be the ANOVA, one sample Z test. Now, to investigate the significance of the difference between an assumed population mean and a sample mean, when either population variance is known, or sample size is large, say greater than or equal to 30. That is nothing but test for single means H naught mu is equal to mu naught. And then the test statistic to test this hypothesis is nothing but as given here. And the decision is if in case it is a two-sided test, then the rejection we will reject this hypothesis if the absolute value of Z is greater than Z alpha by 2, where alpha is the probability of type 1 error. And this test has assumptions, four assumptions. Means this test statistic have been developed by assuming on some assumptions. The assumptions are the dependent variable must be continuous, and then of course this can be verified explicitly. No need to verify this using any statistical tools. Then random sampling from the source population. So this again can be verified by since the way you're going to sample the observations from the population, so that will take care of this assumption. Now the third assumption is nothing but that the characteristic under study should be normally distributed. Of course this has to be verified, and there should be no outliers in the data. I have a real life example here. Suppose the IQ in a certain population is normally distributed with a mean of say 100, and it has a standard deviation of 15. The scientist wants to know if a new medication affects IQ levels. So she recruits 20 patients to use it for 1 month and records their IQ levels at the end of the month. The following are the readings. So these are the readings. There are 20 readings pertaining to each patient, and determine, this is what she is supposed to address, determine if the new medication causes a significant difference in the IQ. Significant difference, that means she is not interested in whether it is greater than or less than. She says that whether there is any difference in the IQ levels after the medication is being given, means whether that mu is different from 100 or mean IQ is different from 100 or not. This is what she is interested. And the same thing, say whatever she is, her objective is to address this issue. So that has been transformed into statistics language, that is mu is equal to 100 H naught, and H1 mu not equal to 100. So again, the test statistic is this one. Under H naught, it follows normal 0, 1. Since sigma is known here, it is specified that this is 15. So hence this is a Z test, and it follows normal 0, 1. And for this example in hand, the mean is 103, the sample mean, and mu naught is already specified, that is 100. Then a sigma is nothing but 15, and there are 20 observations, hence we are plugged in here. So after simplifying this, we do get a value of 0.909, and we compare this value with the, since it follows normal distribution, and you specify your level of significance, say 5%, then reject this hypothesis if this calculated z is greater than z alpha by 2, which is 1.96, or if z is less than minus z alpha by 2, that is nothing but minus 1, or mod z is greater than 1.96. So since here 0.909 is not less than 1.96, we do not reject the hypothesis. Okay, this is one approach. Or you can calculate the p-value, and based on that also you can take the decision. That is, if p-value is less than 0.05, then you reject the hypothesis. So in this case, the p-value is calculated using this formula. It is nothing but 2 times what is the probability that the observed value of the the z value will be greater than the observed test statistic value, that is 0.90. This probability amounts to 0.3632. So this is the p-value. And since p-value is greater than 0.05, hence you don't have sufficient evidence to reject the hypothesis. So in R, how do you do this? How do you carry out this test? And this slide has 2 blocks. First block, it deals with the data set, how to key in the data set, how to store the data set in R, then the other constants which are required to carry out the test. And the test statistic is nothing but the name of the function that does this a test is z.test. It's all lowercase. You know that R is case sensitive, and this z.test is defined in a library or in a package called as BSDA. This is basic statistics and data analysis package. So hence you need to install this package and then load it. So I already installed this package on my laptop, that is R, and loading has to be done whenever you invoke a new session. So hence the loading will be loading that package will be carried out by using this command. Hello.
Yes, sir.
Are you comfortable with this approach?
Sir.
Am I too fast or
Yes,
too
sir.
slow?
Nice, no problem.
Yes, sir.
Nice. Okay, thank you.
So we have a question in the chat box.
Chat box is not visible to me because I'm sharing this screen, right?
Okay, so
see, if they have any doubts, okay, let them speak in between, interrupt me in between. I'll be happy to address those issues. Or if in case they can reserve it for the end, we can address that. What do you say, madam?
Okay, no
see,
issue.
Since I'm presenting, no, I will be not able to see that chat box.
Okay.
Right. Okay. Now the output. See, whenever you run these commands, you get the output. And how does this function works? So this is the function lowercase z.test, all lowercase. The first argument is the data vector which you need to pass it on. The second argument will be the mu naught, and the third argument is the sigma, the standard deviation or population standard deviation. So these 3 are required to carry out the z test. And once you run these commands, okay, the output will be as given in the second block output, and you clearly see that this is the test statistic value. Of course, this is same as the one which is obtained here, and the corresponding p-value is 0.36. So this is how you obtain the p-value. This is the commands to obtain the p-value, 0.362. And along with this, you get other information also. You get related to alternative hypothesis. So true mean is not equal to. So that was the alternative hypothesis. So you get the software itself prints the alternative hypothesis, and also you get the default 95% confidence interval for the population mean mu. So this is the 95%. This is the lower limit, and this is the upper confidence limit. And the sample estimate of the mean will also be given. These are the contents of the output. So we shall move on to the R now. Okay, and I'll execute the commands. Is it visible clearly? The commands are visible, or should I increase the font size? Hello?
Increase the font size, sir.
Increase the font size.
Yes, sure, I'll do it. Where do I have this edit? Yes, how about now? Hello?
Yes,
How
sir.
about
Yes.
now?
Yes. Yes.
Yeah.
Yes.
Yes. So to begin with, okay, if in case you have listed, you know what do you mean by objects in R? Objects in R. So to begin with, we have to clear all the objects which have been previously defined and saved in R. So for that, you can call this function ls and parenthesis. No need to input any arguments. If in case there are any priorly defined objects in the R, so it is going to list them, and so that there should be no accidents. We need to erase all them. So hence, to erase, if there are any objects, then you can remove them by using that rm, and within that, okay, list is equal to ls command, right? Now I'm loading this package library, that package bsda. Now, okay, the command, the data is input to R, and I'm storing in an object X, and then I'll define what is that mu naught. Similarly, what is sigma, and now I'll run this command z.ptest. That's a script, and I do get the output. Yes, this is what you see there. Yeah, now you see that. See how many objects have we created now in this session? Hello, could anybody tell me how many objects we have created?
2.
Three objects we have created. One is x, the other one is mu underscore 0, and the other one is sigma. So hence, okay, if you call this command ls, it is going to list those objects which have been defined right now, which have been created now. So that we need to get rid of this. There are two, as I told, that there are two reasons for having done, okay, for having, the reasons to erase these things or remove this. Then one is that, okay, it is stored, hence it consumes memory, so hence it has to be erased. And the second is that whenever, you know, in the succeeding discussion, if you again define an object, say x, and already you have defined an object, of course it is going to override, but it should not lead to confusion. So therefore it is better always to remove them by running this command remove. Now if you call again this function, you see that no objects have been, okay, created or available. Yes, shall we move ahead? Hello? Yes, are there any
Yes,
doubts
sir.
pertaining to this one sample z test? See, it is not available in this z dot function is not available in any of the default packages what you come across when you download the R software. So it is defined in a package called as BSDA. So okay, hence you need to install and you load it, and then this function will be available for your use. See, I have not verified the assumption of normality. I told you that these two can be verified, of course, by looking at the data. You see that it is continuous, right? IQ, okay, IQ levels is continuous in nature. Okay, no need to verify it. And the second assumption is random sampling. So that will be taken care. She recruits randomly 20 patients. So that random, okay, ness will get into the data. And the third assumption was normality, which I have not verified, and even, okay, outliers in the data, okay, as to we should be also taken care. Of course, I'll not address this. Mainly we'll be addressing this normality. Maybe, okay, I'll reserve it for the next for this test, to sample z test.
Sir,
See, in the previous,
could you please
yes,
tell the full form of BSDA?
b pardon b Basic statistics, basic statistics and data analysis. No, if you install our software, hello, after installing our software, if you're connected to the internet, then you can use this function install.packages, all lowercase install.packages, within parenthesis, key in this BSDA within double quotes. It will get
Thank
installed.
you, sir.
Yes. So the previous one, no, we had only one population there, and pertaining to that population, we were interested in the mean of that population. We had a characteristic that was IQ, say in that example, and pertaining to that IQ characteristic, okay, we had the parameter mean IQ was what we were interested in, and there mean IQ, okay, sorry, there is a mistake here, typographical mistake. Okay, please don't consider this one. Testing equality of means when assuming that the variances are equal, and I have two populations, say X and Y. I am testing the equality of means of two populations. So that is what it says. And here we assume that the population variances are known. Further, we assume that it is equal, and the the population size will, the sample sizes will be large. And the test statistic is this one. This is the X bar A is the sample mean pertaining to say population. Okay, this should have been X. There are many typos, please bear with me. X bar A is related to population X, and X bar B is the sample mean corresponding to population Y. And the sigma square is the common variance. Since variances are equal, so we assume that, and variances are known, okay, the sigma square can be is common, and this is what, okay, is common, and this is what the sigma square denotes here. And you reject this hypothesis if mod z is greater than z alpha by 2. This is for one-sided. Okay, sorry, two-sided. If in case one-sided, then it depends on the, okay, which side, okay, it is greater than or less than. 6 assumptions underlie unpaired z test. It is called as unpaired. Otherwise, it is also called as independent, two sample or two population independent z test, which uses, sorry, this is z statistic. Again, there is a mistake. Okay, what are those assumptions? The dependent variable must be continuous. So continuous pertaining to both the population. These characteristics, no, X and Y, those characteristics should be, we should be able to measure them continuously. Then random sampling from the source population. From both those populations, you should be able to draw, you should draw random samples. Then the data should contain two independent groups. Means, okay, the sample drawn from the population X should, okay, no way be related to the population drawn from Y population. The two populations, the two random samples should be independent of each other. Then the variance of the data is same between the groups. Okay, the variances of the populations of those two populations should be same. And okay, both the populations should follow normal distribution, and there should be no outliers. If we have it, okay, a real life example here. Suppose the IQ levels among students in two different cities are known to be normally distributed, each with population standard deviations of 15. Means corresponding to city A, right? The IQ, the standard deviation of the IQ levels is 15, and similarly corresponding to city B, also it is equal to 15. Means IQ levels standard deviation is 15. A scientist wants to know if the mean IQ level between individuals in city A and city B are different. So she selects a simple random sample. So this has been taken care, simple random sample of 20 individuals from each city. From each city, 20 individuals, and record their IQ values. The following are the readings. City A related, and this is city B related. Determine if the mean IQ level is different between the two cities. And the same thing has been formulated statistically. Mu A is equal to mu B. That is what your null hypothesis. Alternative is not equal to. And the test statistic is as given here. And under H naught, it follows normal 0,1. Since the, okay, standard deviation is specified, no, okay, though the sample size is less than 30, we'll be using Z test in that context. And this is the formula. Variances are equal. And calculating, okay, the required sample statistics, and then plugging in this formula, and further simplification gives me the Z statistic value, that is minus 1.718171. Okay, what are the codes? How do you get this done in R? So these are the set of commands that is required. Okay, I will move on to, what is it? R now. Yes, here it is. Yeah, I'm keying in, okay, the commands. I'm running this command. I'm storing the data, IQ data of those 20 people in city A, in the object city A, and similarly corresponding to city B, other city, it will be stored in city B. The first is, what I do is that I'll plot a box plot corresponding to these two cities. Are you with me? Are you able to see these box plots? Hello? Hello?
Yes, sir, we can see.
Yeah, these are the box plots corresponding to those two populations. This is city A, and this two is city B, and this is the box plot. And this gives, okay, the midline is the medians of those two. Midlines in these two boxes are the medians corresponding to those two cities. And clearly, see, it says that the median corresponding to city B is higher than the city B, right? Hello? And moreover, that is one thing. Yeah, that means that, okay, there is a difference. If in case both were to be normally distributed, then we know that in the case of normal distribution, the mean, median, and mode coincide. So therefore, we can consider them as okay, they follow normal distribution. So in that case, these two lines turns out to be the mean of the corresponding population, sample means of the corresponding populations. So this is the mean corresponding to what is that, the CTA, and this corresponds to city B, and city A has a higher mean compared to this one. But that difference, we don't know whether the difference is true or whether the difference has occurred due to the random sampling. So that has to be verified, and that is why you need a formal test. So see, graphically also we can assess whether there is any difference in the mean IQs between those two cities or not. So this is a graphical aid for comparison, but this is exploratory in nature. We cannot draw conclusions from it. We cannot. So these are graphs, right? Graphs are not conclusive in nature. So therefore, okay, this has to be supported by an appropriate formal test. So hence we go for Z test. And apart from this, there are other information which a box plot gives you. You see that pertaining to this line, no, this is almost symmetric. So hence, some of the properties of the normal distribution. One of the properties is that it should be normal, and hence, okay, this also appears to be normal. But whereas this is slightly negatively skewed. That is what I can make out. Okay, for this, no, to what is it? I see. This is how I got the box plot. There is another way of getting the box plot by using formula interface. This is called as formula interface. IQ is the IQ of all those 40 people, 20 from city A and 20 from city B. It contains, and city is nothing but city A, city B. So to use this formula interface and get the box plot, okay, I have to write some codes, and this is how it is being created. So in R, this city A and city B, they can be called as factors. There is one factor, that is nothing but city type, or city is a factor, and there are two levels of it, A and B. So hence, such a factor such a levels of a factor can be created using this function GL. Are you with me? There is a function called as GL. There are two levels in that factor, and each factor has to be repeated 20 times. And labels of that factor, it has two labels, right? Okay, the labels are city A and city B. So that is how this command works. And I'm going to store that data. It is going to create data. Means you see that city A will be repeated 20 times and city B will be repeated 20 times. And this now city is a factor, and it has two levels, city A and city B. Similarly, okay, I'm preparing the data so that I can get the box plot by using this command, a formula interface command. So for that, first, okay, I've created a factor called as city, which contains 40 readings or 40 elements. First 20 elements are related to level 1, and that is nothing but city A, and next succeeding 20 are related to the other level, city B. Next, okay, similarly, I need to stack the readings, those 40 readings, IQ readings. So for that, no, I'll use this C function, combined function, CTA, comma, CTB, two vectors. CTA is a vector, CTB is another vector. Okay, I'm combining this vector and hence I get a big vector. Okay, and that I'll store that vector in the object IQ. And I use this function data.frame. Okay, this is another data structure. Okay, this okay, data frame wherein I'll pass on IQ and city, the objects which just now were created as arguments into this. This will be the first column and this will be the second column, and it will be stored in an object dat IQ. Hello, hello.
Yes, sir.
Yes, are you following me?
Yes, sir.
Yes, sir.
So this is how I created the data. You see that. Okay, once I run those commands, I do get this data.frame IQ comma city. So first column I have IQ readings, and the second column I have city. The column heading is city, and it has okay. The first 20 observations pertains to city A. Okay, next 20 observations are related to city B. Now, if you call this, okay, there is a function called as names. If you pass this as an argument into that function, it gives you the names of the columns, okay, of the data frame. Now, okay, I'll use this formula interface of the box plot. Now you see. Are you with me? Hello? So on the y-axis,
Yes, sir.
we do have IQ. On x-axis, we do have the cities, city A, city B, pertains to city A and city. So these are the box plots, and from the box plots we can see the whole idea here is to compare between those two cities. So from this box plot I do get an idea. Roughly I get that city A IQ level of city B, or people belong to city B, are high IQ. Their IQ is higher than city B. Let us see whether that okay, the difference, whatever difference, is significant or not. See, you can calculate, if you're interested in calculating the mean of those two cities separately, then you can use this T function and pass IQ, okay, the IQ, the variable for which you seeking mean, I mean whatever that statistic you are seeking, and then the second argument should be the factor. Give you it is going to calculate mean separately for each of those two cities. T apply function. Similarly, you can calculate the standard deviations also. The standard deviations are likely, though, okay, we say that the standard deviation is 15, it's slightly different. And then, okay, I'll come back to this one. Yeah, this is what we have done so far. You can even, okay, what are that, test whether the, yeah, I'll do this after a while. First, let me complete this one, Z test. Yeah, this is the Z test. I'm done with this. I've explained you what you mean by this script, and this is the output. Okay, the command that is used to carry out two sample Z test is X is equal to city A and Y is equal to city B. So you have to specify, okay, the observations corresponding to city A and city B separated by comma. That will be your first argument. The third argument will be, okay, the mu is equal to 0. That means that you're testing that city A, city B not equal to. Am I right? I mean, they are equal to. So therefore, okay, the mean will be equal to 0, and specify the sigma corresponding to both those populations, standard deviations corresponding to those two populations. So this is the syntax, okay, that you need to take care while performing this two sample Z test. And this is the Z test, statistic value, and the corresponding p value is 0.08. Since the p value is greater than, okay, say your alpha is 5%, means p value is greater than 0.05. Hence, you do not reject the hypothesis and okay, conclude that the two cities, no, they do not differ with respect to their IQ level. Are you with me? The people belong, so the IQ of the people belonging to those two cities, no, they do not differ with respect to their IQ level. Shall I proceed? Hello?
Sir, sorry to interrupt you. There is a question regarding the p-value. So,
Yes, madam.
can you please define what is p-value and how it is interpreted?
Say p-value is how do you define p-value? Just a minute. P-value is defined as it is the probability of getting a test statistic value as extreme as the one observed. Are you with me? Hello. Okay, this is what vocabulary, how it is defined. When it comes to using notations, see what is the statistic here? It is Z, right? Hello? The statistic used here is
Yes,
Z. And the test, okay, the test statistic, it follows standard normal distribution, right? So therefore, to calculate this probability, we give probability of that Z, uppercase Z, greater than or equal to or greater than minus 1.782. Are you with me? Hello?
Yes, sir.
yes, sir.
Okay, what is mod Z greater than, okay, greater than minus 1 point, sorry, Z greater than minus 1.71718. That is how you calculate the Z value. Of course, here in this context, since Z follows normal, standard normal, and it is a two-sided test, so hence it has to be multiplied 2 times. Are you with me? It is the probability of getting a test statistic value as extreme as the one observed. What is the probability that Z value will be greater than the one observed in this context? So that is Z value greater than minus 1.718. Hello? Are you through with this?
Okay, sir. Yes, sir. Yes, sir.
Okay. And in R, it can be calculated. See, this people, that is why I had a separate slide here. Okay, at the beginning to discuss this p value. What is this p value? I had that. Yeah, this one. And when it comes to the computations, no, you should be aware of the test statistic and what distribution the test statistic follows, null distribution of the test statistic, and the value of the test statistic. And further, you have to use, okay, whether it is one-sided or two-sided. Are you with me? All these concepts are required to calculate the p-value. Yes. So we are through with this second problem, except that, okay, we have not verified the assumptions. Okay, now I'll do it. Assumption one was that, okay, I mean, there were 6 assumptions. Assumption one was that, okay, it is continuous. Of course, IQ is continuous, no problem with that one. The second one was random sampling. Yeah, it depends on your study design. If in case I explained them here. See, no need to verify assumption one, it is evident explicitly. Assumptions 2 and 3 can be taken care of during the study design. 2 and 3 deals with, see, the random sampling, and the data should contain 2 independent groups. I mean, the data should come from 2 independent. So CTA should not get influenced by CTB. So that is all. Okay, hence this can be taken care during the study design. Whereas 4 to 6 have to be verified. Each of these assumptions 4 to 6 can be tested graphically or by using formal tests. You can even, okay, there are some tests pertaining to outliers also, which I'll be not discussing. So there is in the literature, you can even test whether like a given set of observations has an outlier or not. Of course, your box plot will be sufficient. Okay, graphically also you can assess, okay, there are any outliers in the data or not. To assess normality, it can be done either graphically or using formal tests. Graphically in R, you can, okay, go to plots or histograms or density plots. Or even, okay, and when it comes to variances, equality of variance, that is nothing but homogeneity. You can use box plots or histograms or even density plots. So here comes the, okay, normality check pertaining to that data set. Okay, we should check for the data set. Okay. Right here. I do get the normal QQ plot corresponding to those two. What is that? Just a minute, sorry. So one after the other, control R. Yes. So this is the normal QQ plot corresponding to the sample of CTA. And how did you get it? QQ norm is the function. So when you run this command, see, 2 or 3 commands can be at a time executed, provided each command is separated by a semicolon. Are you with me? Hello? Hello? In R, a set of commands, if in case they are separated by a semicolon, they can be executed in one go. What does this command gives me? This command just, okay, prints the theoretical quantiles against the sample quantiles. Are you with me? And since I've used QQ normal distribution, so it calculates, it gets the theoretical quantiles from that normal distribution, and okay, it calculates the sample quantiles using this data, okay, and plots it. These points are obtained, okay, using those theoretical uh, and sample quantiles, and a reference line has to be drawn, and that will be done by this QQ line. A reference line has been drawn. And coming on to the interpretation of this graph, if most of the points are lying on this line, then okay, we can interpret that the data follows normal distribution. Otherwise, okay, there is a deviation. Of course, there is a slight deviation here, but not to a great extent. Are you with me? Hello? Most of the points are very close to this line except at the tails. At the tails, right? And similarly, corresponding to the second data set. So this is up, okay, not much, but still, okay, there is a slight deviation corresponding to this one. I mean, the second set of data. Then verifying whether the variances are equal or not. For that, again, I'll resort to this box plot. Yeah, see this box plot, no, the line, okay, it has two whiskers, right? These are called as the whiskers. Okay, this will be the maximum, and this will be the minimum corresponding to city A, and this will be the maximum corresponding to city B. Minimum and maximum. So this gives you a rough idea about, okay, the range of the possible values what you see in city A, and this gives you the range. So here it is clearly evident that the range of the values of city A is slightly lesser than that of city B. That means that, okay, city B data related to city B is more, okay, the variance of city B is more compared to city A. So a rough idea about the variances, you get it from the box plots itself. Hello. Apart from this, you can use a formal test also to test whether okay, the data follows normal distribution or not. For that, there is, okay, a test called as Shapiro.test. Shapiro, Shapiro. This is a test exclusively meant to test for normality. So I'll pass that as a third argument into this function T apply, because I have to separately carry out this normality test for okay, CTA and CTB data set. Yes, I do get this result. Okay, are you able to see this? Yes, hello? What can you make out from this one? As I told that, okay, for CTA, this is the test statistic, Shapiro will test statistic value, and this is its corresponding p-value. And for CTB, this is the test statistic value, and corresponding p-value is this one. So from this, it is clearly evident that, okay, see, the null hypothesis will be the data follows normal distribution. Here, since the p-value is less than, say, 5%, then you reject the hypothesis and say that the data will not follow normal distribution. And whereas this follows normal distribution, just slightly, okay, but it is at the verge of, okay, rejecting the null hypothesis, but still we can consider them as normally distributed. Similarly, you can carry out the variance test. So this is what the theory pertaining to Shapiro will test. This is the test statistic, how it is been calculated. W, Xi's are nothing but the ordered random samples, and Ai's are the constants generated. It involves a lot of mathematics, just okay, to get an idea how the test statistic look like. The Shapiro will test. This is a very commonly used test statistic to test normality. So reject S naught if W is small. Then coming on to the variance homogeneity check. Okay, we can use this variance dot test. So this is the test for equality of variance. That is nothing but our usual F test. It is a ratio of the sample variances of the two populations, S1 square divided by S2 square, and this is how the decision is taken here. And the results, no, okay, this test is performed using this NAR, using this function var.test, testing equality of variances. So this is the F value and this is the P value. Okay, we assume that the variances are equal. So that is what, okay, the way null hypothesis. Alternative will be not equal to, since p-value is greater than 0.05, say at 5%, we do not reject the hypothesis, and hence the equality of variance assumption is satisfied. Hello? Hello? Hello?
Yes, sir.
Yeah, I think, am I clear to you?
Yes, sir.
Hello?
Audible.
Yes. Okay. Next, we should go ahead and see the simple, okay, t-test. See, t-test is used when the sample size is small and population variance is unknown. The test statistic is as given here. Then reject H naught if MAT is greater than T alpha by 2. Okay, as at alpha level of significance and n minus 1 degrees of freedom. These are the assumptions pertaining to t-test. And okay, here is a real life example. Okay, kilojoules. Here is an example concerning daily energy intake in kilojoules for 11 women. Okay, you might wish to investigate whether a women's energy intake deviates systematically from a recommended value of 7,725 kilojoules. So this is your mu naught. N is small size and variance is unknown. And we assume that the data follows normal distribution. So these are the hypotheses, corresponding hypothesis, and the test statistic. And it follows under H naught, it follows T distribution with n minus 1 degrees of freedom. And the test statistic value is minus 2.82075. And how do you do this in R? These are the commands. Okay, daily intake. And I have specified the mu, n I know, x bar and t. And this is the inbuilt function to carry out the t-test. The first argument should be the data. Second argument should be your mu naught. The third argument should be your two-sided or one-sided, whatever it is, and it gives you, okay, the output of this nature. And the test statistic value is this one. The corresponding p-value is 0.018, which is less than say 0.05. Hence, you reject the hypothesis and hence claim that okay, the mean intake is not equal to 7,725 joules. See, you can even, okay, this is for two-tailed. Okay, the default is always two-tailed. Even this also gives you the same result. You see that though I have not included the third argument, this argument in this command, okay, there is no difference in the output. That means that the default will always be a two-sided test. What if in case I want to do an alternative, okay, say greater than? So in that case, okay, it means your alternative hypothesis is nothing but mu greater than 7725. So in that case, I have to pass this argument. See, the default, it always gives you 95% confidence interval for the mean, population mean. So you can change that also. Say if you are interested in 90%, then 90%. I made those two changes. One is, okay, I'm testing whether H1 mu is greater than 7725. Yeah, it is clearly evident here. You see here. And I do get 90% confidence interval. So the NP value, I'll skip this part, right? Okay, symmetry. Yes. How about normality corresponding to that one? Normality has to be checked corresponding to that. See, it is normal, almost normal. All the points are falling on this line except this point. So hence the data follows normal distribution. So this is how the decision is made, and this is what your normal QQ plot. All the points are, and the commands used are this one. Unpaired t-test. So I'll skip this part. Okay, this is the test statistic. Okay, to test. Okay, equality of two means when the population variances are known and they are equal, we assume that they are equal and the sample size is small. Mu x is equal to mu y. And okay, we have S square here, which is the pooled sample variance sample variance, and that is okay calculated using this formula where S1 square and S2 square as the sample variance corresponding to X and Y populations respectively. And okay, reject H naught if okay mod is greater than this value, and okay, n1 plus n2 minus 2 degrees of freedom. And this is for two-sided. Okay, these are the assumptions corresponding to t-test. Of course, the assumptions are very much similar to the Z sample, Z test, two samples. Okay, here is the data set. I do have two genes. I think two genes, not two genes. It is plants inoculated and uninoculated plants, and their readings. That is nothing but the what is this? soya bean inoculated with nitrofuran bacteria yield more. And so the growth, this is the growth. That is nothing but the pod weight. Pod weight corresponding to those 8, what is that? 8 plants. Okay, under this inoculated setup and uninoculated, these are the readings, and the corresponding means and their standard deviations are given in this table. Now the question is there any statistically significant difference at 5% level of significance, say, between the mean pod weights for the two groups, that is inoculated and uninoculated? So first we shall graphically we shall plot and get an idea whether there is any difference or not. Yes, it says that there is difference. Okay, you see that this is the box plot corresponding to that inoculated group, and this is the box plot corresponding to uninoculated. And on the y-axis you are the pod weights. It's clearly the inoculated group has a pod weight higher at a higher level than that of the uninoculated group, right? So there is it appears that there is a difference in the mean, but we don't know whether this difference is statistically significant or not. So that is one thing. And this is slightly, you see that the box plot, from the box plot it is symmetric, and hence it may be normal. And moreover, the variance are also equal. That is what we can make out from these two graphs. When we compare these two graphs. And there is one more thing. There is an outlier, in this group. Since it is you see a dot here. And for this, this is the test statistic what we get, right? Normality of test has been taken care here. So we are testing whether the the variances are equal or not by using that var.test, and the output is as given here. The p-value is 0.62. Wait, what is that? Yes, we have here. I'm keying in the data. I'm calculating the summary of those two groups. This is group 1, group 2. Similarly, there is a library package called as psych. In the library, there is a there is a function called as describe. It gives you a lot of descriptive statistics pertaining to the data. You can use that. So first, we shall verify whether the by using the variances are equal corresponding to those two tests, those two populations are not. It says that yes, it is. We do not reject the hypothesis, so hence it is equal. So population, we have verified that. Verifying separately, the normality also, you see that a very high p-value you get. You do not reject the hypothesis, hence normality assumption is also satisfied. Now we'll perform the t-test. The formula to calculate the function that is used to calculate or get the analysis done is t.test, and the first two are the vectors, the samples in the objects in which you have the samples, and you assume that the variances are equal, right? This is the test, the output. Yeah, this is the output what you get, and the p-value is 0.03. So what does it says? There is no difference. Yes, there exists a difference because you reject the hypothesis. That was already evident here also in the graph. You see that I told you, there is a difference. So that is confirmed there. Right? This is how the decision making is done. So if in case the alternative is greater than, then use this. Alternative should be greater than. You can change the confidence level similarly. And so you can use even formula interface also, t.test here. Right? For that, again, data has to be prepared. So this is how we prepare the data. And here you have t.test pod.weight. It depends on nitrogen fixation. Means whether it is fixed or not. And we assume that the variances are equal. Next, coming on to the test of equality of two means when the variances are unequal. This is called as Barron's-Fisher problem, and the test what we use is nothing but Welch test, and this is the form of the test statistic. We don't use the pooled sample variance here. We use the various sample variances separately here in this. And further, there is a slight difference in the degrees of freedom corresponding to this statistic. It is nu, where nu is calculated using this formula. So this, how do you do this in R? What is that is, what I have done is that I have simulated observations from normal distribution, 500 observations with mean 5 and variance 2 or standard deviation 2. And I'm going to draw a sample of size 10 from this using this function and then store in sample 1. Similarly, a normal distribution, 500 observations I'm going to generate, mean this and standard deviation 4. I'm going to draw a sample of 8 out of this 500 observations and store that in sample 2. and I'm going to prepare the data. Okay, this is how it is being prepared. So I use a stack here. Stack, you know that you arrange one above the other. And list is a data structure, wherein I need this sample one, sample two, what is that, observations. And now I'm going to change the names of these columns of this object D. I'm going to call D. So you'll see that that is reflected here. Right. The first 8 observations, 10 observations correspond to sample 1, and next 8 corresponds to. And okay, what is this subject of marks? Okay. Yeah, I do get an error here. You see that when I run this command, I do get error. So to draw the box plot, I've used marks, the formula interface. So I'm calling by names of the columns. Since the names of the columns are not available, I do get the errors of this kind. It says that object marks not found. So therefore, okay, you have to attach that object. Now, if you attach this object, then you can extract whatever columns you want by calling their names, column names, using their column names. So hence, okay, now I got it. Now you see that the orientation of the box plot has been changed. Earlier it was what is that? What is vertically it was plotted, now horizontally, so that comparison becomes easy. You see that, okay, yes, there is a slight difference in sample 1 compared to sample 2 with respect to the means. How about the variance? You see that the variance of sample 2 is higher, bigger. It has a larger variance than sample 2, because the way in which I generated the observations from there itself, you will get to know sample 1 standard deviation is 4, whereas this is 2, whereas this is 4. Hence, sample 2 variance is higher than. So variances are unequal corresponding to these two populations, or the samples from which the populations from which these samples have been drawn. There is the difference in the means also, but I don't know whether this difference in the mean is significant or not. So therefore, we need to conduct the ET test, and this is how it is being conducted. You see that now variance dot equal is equal to false. I'll use this. It says that yes, okay, you do not reject the hypothesis and say that the means are not equal. Of course, the means of the two populations are same. It is 5 and 5. So whatever the change in the sample mean you saw here, sample mean, okay, there's a slight change in the sample means. So that can be attributed due to the random fluctuation. Yes, I'm through with this. I'll move on to, hello, madam. Madam, are you there?
Yes, sir. Yes,
Hello?
sir. I'm there.
Yeah, it's already 11:09. How long can I go?
So it's till 11:20, but you can take till 11:30, no issue.
Yeah, thank you.
Yes.
Thank you. This is the output of the Welch 2 sample t-test. You see that variance var dot equal, we need an extra argument, var dot equal is equal to false. If you don't key in this command, if you don't key in that command, or that argument, okay, even in that case also it is going to calculate the it is going to carry out the Welch t-test. Means the default settings for the variance dot equal is false. So if in case you want to carry out the 2 sample t-test, assuming that the variance is equal, then explicitly you need to pass that argument var dot equal is equal to true. Let me remove the objects what I have created. So we shall move on to the paired t-test now. Yes, paired t-test. So they investigate the significance of the difference between the means of two populations which are correlated. See, in the earlier case, the previous one, we assumed that the populations are independent. Okay, there is no interdependent between the two populations, or correlation does not exist between the two populations. They are not dependent. When they are dependent, then the slight modification has to be done for the. You see, your goal is to compare the population means of two populations. If the populations are independent, then it will be a problem. Okay, it will be a case of independent samples test. Okay, whether if you know the variances, use the Z test. If you don't know the variance, or either if your variances are known and they are equal, Z, or if in case the sample is large, go for Z. Otherwise, in the sense variances are unequal and sample size is small, then go for sample t-test. If in case they are dependent, then what is the way out? Okay, it is the paired t-test. Something of this design before and after. okay, such a sort of study, repeated measures study, wherein you repeatedly take readings on the same individuals before and after, or at two different time points. So for such designs, and you want to compare the means for such designs, okay, then you use this parity test. Test for equality of two means when the two populations are correlated. So that is nothing but mu d. D is nothing but the difference between those two populations. We assume that it is equal to 0. The test statistic is as given here. Okay, d bar minus mu d. D bar is nothing but the sample mean of the di values, where di is nothing but xi minus I. I goes from 1 to n, and then xi is the readings. Okay, first readings, and a set of, you see, you have paired observations here. So okay, pertaining to each observation, I have two readings. So the difference between those two readings is nothing but xi minus yi. Each reading is our ith observation is nothing but xi minus yi, and that will be denoted by di. And corresponding to this di, I calculate the variance, and that will be denoted by sd square. And the reject for two-sided test, reject h naught if mod t is greater than t alpha by 2 n minus 1. Again, okay, these are the assumptions corresponding to this parity test. Random sampling. Okay, data must consider two related groups or matched pairs. Okay, this is the earlier one. Okay, earlier you had the independent. Now they are related. Then the variables should be normally distributed, and there should be no outliers. So here is a real life example. But blood samples from 10 people were sent to each of the two laboratories. You see that it is not repeated, but same individual, lab 1, lab 2. So that is matched pair. Okay, or related. It turns out to be a related pair. And okay, lab 1 readings, I will denote that x by x, and lab 2 by y. And I take the difference between these two, I do get d readings. These are the d readings. Then, okay, this is the x bar, this is y bar, and this is z bar. And the sample standard deviation corresponding to this d is nothing but 5.21. Plug in those values here, and okay, in that formula which we saw, okay, in this formula, and then it boils down to a number. Okay, further simplification, it gives you minus 4.49. Okay, this is the test statistic value. You, okay, say at 1% level of significance you're going to do this. Then reject h naught if t value is greater than t, okay, alpha by 2, that is 0.005, and the degrees of freedom is n minus 1. N is 10 here, so it gives you table values 3.25, or if, okay, minus, okay, due to symmetricity, minus 3.25. Since this value is lesser than this value, we reject the null hypothesis. Or you can use p value approach. For p value for this case is, okay, for this problem is 0.001509, which is less than 1%. Hence you reject the hypothesis, and hence claim that, okay, the blood samples, okay, from each of the cholesterol level, okay, they do differ between the two laboratories. Okay, how do you do this in R? Okay, laboratory 1 readings, okay, the cholesterol readings of laboratory 1, I'll store that in object lab 1. Similarly, lab 2 readings will be in lab 2. Then d mean, okay, see the test statistic value. Okay, now in R, how do you do this? Again, you use the same function t dot test lab 1 readings, comma, lab 2 readings. These are the first two arguments, and that will be followed by the third argument, where now it is called paired is equal to t, or just true also you can key in. Paired is equal to true. It is going to carry out the parity test. So this is the test statistic value. It is same as this one. Then this is the p value. Okay, p value is less than, say, at 1%, it is less than 0.01. Hence you reject the hypothesis and claim that, okay, the true difference in, okay, in the mean or that cholesterol levels are not same, they differ. Similarly, you can carry out one-sided also by, okay, keying in one more argument into this same code command. Okay, alternative less than or equal to, you do get the, okay, corresponding. You will see the true mean is greater than 0. True mean is less than 0. Here it was not equal to 0. This is two-sided. Means the d, mu d not equal to 0, mu d greater than 0. Oh, right. So when do you say, okay, what is it? How do you interpret this one? When will somebody be interested in testing this hypothesis? Mu d greater than 0. Could anybody help me out? Yes, shall I proceed? Hello? Hello.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So we have come to the last one. This contains too much of stuff. ANOVA. ANOVA, this was developed by Fisher in 1925. So it's a very powerful statistic and a core technique for testing causality in any data. It need not be only in biological data. So researchers use ANOVA to explain variation in the magnitude of a response variable of interest. One way it uses, okay, this is nothing but an extension of the t-test. Two sample independent t-test. Test the equality of population means more than two when classification is by one categorical, one way ANOVA. The classification variable factor, okay, we call it as an independent variable, which is categorical in nature, and the response will be continuous, sometimes even discrete also, but it depends on the data. And one way ANOVA extends the two sample t-test for testing the equality of two population means to a more general null hypothesis. Although termed analysis of variance, ANOVA stands for analysis of variance, aims to identify whether a group of, see, if you go by the name, no, you'll be deceived. It is not actually, it is testing equality of variances. It is actually testing equality of means. So hence, it is such words are called as misnomers. ANOVA, in fact, what it will be doing is that it will be making use of variances to test for the equality of means. It will be analyzing the variances and hence testing the equality of means. So therefore, it is named as analysis of variance. Okay, this is how the model looks like. This is the response. This is the overall mean. Then this is the tau I is the ith treatment effect, and epsilon ij is nothing but the error component. It can be seen as a model, linear model, right? Why do you have these errors? Okay, due to this, these are the reasons. Then we are testing actually, okay, but assuming that there are k treatments, right? And okay, n observations with n observations per level means equal number of observations at each level. It is a balanced design. Mu1 is equal to mu2 is equal to mu k. At least one is inequality, one equality is not satisfied, or you can even test. So to test this, okay, you use ANOVA, and these are the assumptions. Random sampling from source population means if you see how many populations are there, from each of those populations you should draw a random sample. Further, each sample should be independent of the other. So that is what the second. And the variances of all those k populations should be, they are unknown and they will be equal. That's what. So that is called as homogeneous variance. And each of those populations should follow normal distribution. So these are the main assumptions corresponding to one way ANOVA. If the above hypothesis assumptions are valid, the ANOVA procedure is an exact test of hypothesis of no difference in the means. See what happens if in case that normality in each of those previous discussions, if that assumption is not satisfied, then the value of the test statistic under the null, the null distribution of the test statistic, okay, will not be correct, and your conclusions will not be valid. So therefore, assumptions are as important as the, okay, main objective. So unless and until you don't verify the assumptions, you cannot blindly so apply the test, and based on the end results you can just okay, draw the conclusions. They are only valid when you verify the assumptions. So what is the philosophy behind ANOVA? There are two, okay, basic idea is to partition total variance of the data into two sources, that is between and within. So if the, okay, SST is the total variation, it will be decomposed into between and within like this, and wherein the SSB, okay, this is the degrees of freedom associated with the between, and within it is n minus k, and SST it will be n minus 1, where n is nothing but, okay, a summation lowercase ni, I going from 1 to k, and you calculate the mean squares by dividing the corresponding sum of squares by their degrees of freedom. Hence you get MSB, MSW, MST. So this is an estimate of the variance between the k treatments, MSB, whereas MSW is the variance of the estimate within each of the k treatments, and this is the overall variability in the data. And the test statistic is the ratio of the group treatment and the error mean square. This is the F test. So under H0, this follows F distribution, and the table, okay, will look like this. Critical value for rejecting region is this one, upper tail alpha percentage point of the F distribution with k minus 1 comma n minus k degrees of freedom. So this is the one way ANOVA table. Okay, this is how you take the decision. Now assumptions again. Okay, we need to verify the assumptions. So the first two assumptions are primarily a function of the sample design, random sampling and independent measures. Okay, while the later two are functions of the populations under investigation, therefore are generally beyond the control of the researchers, and you need to verify whether these assumptions are. Okay, this can be taken care of, whereas these no, they have to be tested whether they're even independent can also be tested by using some run test, sign test like that. There are some tests. So here is a real life example. Okay, to investigate the inheritance of maternal influences on the growth of the rat. In the study, rat litters were separated from their natural mothers and they were nurtured by foster mothers. Mothers and litters can have four different genotypes. Genotype A, B, I, J. Suppose we want to investigate whether weight gain of the litter in grams at age 28 days is related to foster mother's genotype. Lat litters were separated from their natural mothers at birth and given to foster mothers. For this, we could use one-way ANOVA procedure to compare the means of weight gain across different groups. Now, this is one group, this is group. So there are four groups, and we want to compare the gain in the weight. Okay, weight gain. Okay, whether the mean weight gain in between these four populations are okay equal or not. So here weight is the response variable and the mother is the factor. So or the genotype is the factor. Okay, this is the commands that are used to carry out ANOVA in R. For that, first, no, we need to prepare the data. So this is how the data is prepared. Okay, I'll key in this data. Then I'll use the stack function. I'm going to list. Okay, within that stack function, I'm going to use this list so that okay, I can one above the one below the other in the same order. I can what is it? Arrange the entire data set. Okay, let me run this command. Yes, I do have the data. Now I prepare the data. It's a data frame. First is value. This is nothing but the weight gain, and this is the mother. So our genotype, I'll change that names as well. Now you see that I do have the weight gain and the genotype are the mother. Okay. So whenever I ran this command, no, okay, if there are many observations, nearly 61 observations are there. 61, there's a typographical, I think. Okay, one has been extra. Okay, don't worry. Then structure of the data, you can see what is the structure of this data. So it is a data frame. It contains 61 observations of two variables. Variable 1 is weight and variable 2 is genotype, whereas the genotype is a factor having four levels, genotype A, genotype B, likewise, right? And whereas weight is a numeric vector or a data type is numeric. So the str function gives you an idea about okay the data, what type of data you have, what are the variables, likewise. Now first I'll plot this box plot. Yes, attach, and I'll try to compare between those. Okay, but compare the weight gains between those different mothers. Okay, you see that J, no, genotype J mother has a less weight gain compared to B. B has the highest weight gain in B. Okay, genotype B is higher compared to rest of the other, and this has the least. I don't know whether this is significantly okay. This amount should maybe okay somewhere the mean falls here, whereas this has here. There's a lot of difference. Okay, there's a much difference between these two compared to A and A and B. There is no difference. A and B. Sorry, A and B. There is no much difference. B and I. Yeah, the difference is there, but statistically significant or not, we need to explore it further. You can have the concept of notches also in histogram. Okay, since I'm running short of time, I'll not discuss this notch concept when it comes to box plot. You can explore it. Yes, ANOVA, I use LM function. There are many ways of carrying out ANOVA. LM is one function, right? LM, you see that weight depends on genotype. The data is what the second argument which I pass on to this LM function. I store that results in res underscore ANOVA, and then I'll pass this as an argument into ANOVA function, and I do get this ANOVA table. Hello? So genotype, degrees of freedom, And these errors are residual. This is the degrees of freedom corresponding. Your sum of squares, mean sum of squares, f value, and the corresponding p value. Yes. Yes, box plot. This is how you get the box plot, and this is the ANOVA table. Okay, these two commands will give you the ANOVA table. So this is what you see here. Right? Yes, this one. This is the ANOVA table. So you see that the p value, it has been flagged with 2 stars, means it is significant at, okay, not even 1%, 0.01% it seems. Sorry, 0.1%. This is significant. Okay, highly means there is a difference in the mean weight between those 4 mothers, genotype A, genotype B. That is what the conclusion. So hence you reject the hypothesis and then conclude that, okay, there is a difference. Okay, hello. See,
Yes,
there
sir.
is another way of understanding or getting more insight into this ANOVA concept. It is available. That function is available in. That function is available in a library called as Granova, graphical ANOVA. So you have to install this package, and then, okay, use this function grano dot one w. You pass this to as the argument, and you see that, okay, it gives you this information regarding what is the overall mean, okay, and then difference between also degrees of freedom between, degrees of freedom within, then mean squared error between, mean squared error within, then f ratio, okay, then the probability. Are you with me? Then, okay, corresponding to each of the different mothers, it gives you the contrast, mean, difference, and other things. Okay, but apart from this, the important one is this one way ANOVA, graphical ANOVA. Hello? Yeah, this is the graph what you get. Okay, you see that something, it is it's a one-dimensional graph. See this red part, no, it gives you the total variance between, and the green, this blue area gives you the variance within. Okay, it is clearly evident that the between variance area is very much bigger than within area. So hence, okay, you reject the hypothesis. That is one thing. And okay, this the first okay, group J, you see that, okay, these are the observations, 10 observations which have been plotted, and this is the scale, and you have a triangle here with, okay, red color, that is nothing but the mean, sample mean corresponding to genotype J. And similarly, okay, this corresponds to genotype I, and this corresponds to genotype A, and this corresponds to genotype B. So it is clear that, okay, as you move from J to I to A to J, okay, the mean, okay, is, okay, the mean, no, the sample means they are in the increasing order, and they are falling on a straight line. And this green dot is nothing but the overall mean, overall grand mean. The grand mean is 54 here. You see that? And this is the group J means, group I mean, group A mean, and genotypes B mean. This is, so this, as I told that, this, okay, this denotes, I mean, this blue box denotes the mean squared error within, and the red, okay, one denotes this one. I have statistic value, likewise. So there is a lot of information regarding this one way ANOVA. From this one way ANOVA itself, we can interpret this, okay, from various angles. So this gives you an idea. See, this gives you an idea about the scatteredness variance corresponding to genotype B. This one. This is called a stack plot. Strip chart, sorry. Strip chart. Yes. Now, okay. How do you verify the assumptions corresponding to this? There is a function called as plot, and pass this res ANOVA object as an argument. It gives you 4 plots, so that to get all the 4 plots in one window, what I have done is that I have partitioned the graphical window into a 2 by 2 matrix, so that all the 4 plots I get it in a single window. So this gives you the normality, assessing normality, the second panel, first row, second second column, okay, whatever it is nothing but it corresponds testing whether the errors follow normal or not here. And this, no, it is linearity assumption, and as well as even the variances are equal or not. These two does the same thing, and this gives you an idea about whether there are any outliers in the leverage point and outliers in the data or not. Of course, for this problem, for this data set, I don't see any violations with respect to the assumptions. Or you can carry out Shapiro-Wilk test. You see that, okay, for all the 4 groups, okay, we do not reject the hypothesis. That means normality assumption is satisfied. Then how do you test test for equality of variances? The graphical box plot or QQ plot. I'm sorry, this is there's no QQ plot here, only box plot. So you can use Bartlett test or Fliegner-Klein test and Leibniz test. Bartlett test is explained here. This is how the Bartlett test is done. And in R, okay, there is a function called as Bartlett.test, and this is a formula interface, and this is the data in which, okay, these 2 columns are available. I'll conduct that. So this is the output. Okay, this is the output. It says that the variances are equal, right? Variances are equal of all those K populations. Not true for at least 1, right? Since p-value is greater than, say, a level of significance, your chosen level 5% or 1%, you do not reject the hypothesis. Hence, the assumption of homogeneity is satisfied. Then, okay, here it says that, yeah, normality. I have used only Shapiro-Wilk test, but in R, no, or in the literature as well as even in R, there are some. Okay, I don't know how many are there. I have listed only 16 here. This slide sheds light on that aspect. Anderson-Darling test, Kramer-1 Mrs. test, Lilly-Ferris test, Pearson chi-square, Shapiro-Francica, Gary test, likewise Jarg-Bera, kurtosis test, Kunis test, Weisberg-Bingham test, Kolmogorov test. These are some of the tests that are available in R to test for exclusively for normality. And this, okay, there is a package called as norm test. In that package, most of these different statistical tests meant to deal with normality is defined. You can explore them. Yeah, this is regarding the Shapiro-Wilk test for the corresponding to that data set. See, ANOVA, it says that yes, there is difference. Yeah, we got to know that, okay, the mean, there exists difference in the mean, but we don't know between which okay, has led to the rejection of the hypothesis, between which populations there exists, okay, significant difference. To tease out that source of significant difference, we carry out post hoc test. Okay, ANOVA is a preliminary test. So in order to tease out the source of significance, we carry out post hoc tests. So they are called as multiple comparison tests in the literature. The methods examine or compare more than 1 pair of means at the same time. If that is insignificant, then the question of using post hoc does not arise. So here is a table which sheds light on that aspect. There are many post hoc tests. So when to use which one? So in this case, okay, the population, the sample sizes were equal and the variance are also equal. So hence, in that case, you can prefer Tukey's HT. Tukey's HSD is defined in this manner. This is how you get Tukey's HSD, where Q is defined as a student range statistic. MSW is a within what is that, mean sum of squares, and N is the number of observations. The sample size of the groups compared this one. So in R, how do you carry out this post hoc test, Tukey's HSD? For that, no, yeah, I'm going to make use of another analysis of variance function, that is AOV. Use this formula interface. Hello, madam. Hello, madam.
Yes, sir.
Madam, are you there?
Yes.
Another few minutes. I'll wind up. This is my last
Okay.
discussion. Bear with me. Okay, I'll store that outcome in this what is it in this object model. I'll call this summary of this. Okay, I do get the same one-way table. Now I'll pass this same model as an input into this Tukey T capital, HSD all lowercase. Okay, and I'll specify the confidence interval, whatever confidence interval, 95% confidence. So I do get, so pairwise comparison. Genotype B versus genotype A. This is the difference in the mean. You get the 95% confidence interval, and whether there is any difference or not between these two. Okay, p-value, adjusted p-value is what we get. So there is no, it says that there is no difference between A and B. Already it was evident in the graph also, right? See, when we plotted the graph box plot, I told you that, okay, there is no difference. You see that A and B, there is no difference. So that is what even this also sheds light on. Similarly, I and A, these two, there is no difference. J and A, J and also A are slightly, okay, yes. Say maybe at 10% it is significant, at 5% it is insignificant. This is what it says. Coming on to J and B, B and J. B and J, it says that, yes, yeah, where am I? I and B. I and B, there is no significant difference. B and J, yes, it says that it is significant difference. So except between B and J, between other pairwise comparisons are insignificant. So only this has led to the significant difference in the, that is the reason why, okay, in ANOVA it was rejected. We are through with this. Next is, okay, this is some, okay, related to post-hoc test, when to use which test. This sheds light on, right? Okay, yeah, these are some of my references which I've used for my preparations. Dalgard is a beautiful book on okay, statistics with R, and even Varzani. It is available. The PDF is available. You can download it. This is the book which we have written along with Prabhanjan and Manjunath, a course in statistics with R, Wiley publication, published in the year 2016.